And welcome to the 22nd of April. This is a GCSE and A-level physics live stream. If you are an A-level student, then I'm going to be live from 8 o'clock going through some questions. You can find all of those at alevelphysicsonline.com/live. If you want to find the material for the GCSE stream, so if you want to download your own copy of these papers, head over to gcsephysicsonline.com/live. And that means you can actually buy and download your own set of these papers. Now, something else that if you're an A-level student, if you have a look at the top of the chat in the live stream, there's a link to the A-level physics derivation sheets. And I'm going to put this link up in the comments beneath this video after it's gone out on YouTube. And basically this allows you to download a complete booklet of derivations for A-level physics. So this is, I think it's about 40 of them in total. So if you want to download this booklet completely for free, you can do that. And it basically looks exactly like this. And it has some of the most important derivations for physics, for A-level physics, and you can download that just by following the link. Well, I'm going to be talking a bit more about that at 8 o'clock. Okay, and of course, these live streams are not specific to one exam board, although at the moment I'm mainly covering topics which are going to be coming up in the paper 1 for AQA. But ultimately, most of the GCSE and A-level physics I'm talking about is going to be suitable for anybody doing whichever exam board. It's only really the structure of the exam that changes. So today, we're going to be doing, we're going to be doing some topics which come from paper 2. Okay, so these are paper 2 AQA GCSE topics, but we're going to be looking at two things. First of all, we're going to be looking at infrared radiation and black bodies. And then secondly, we're going to be looking at the refraction of light. And this practical here, looking at rays of light going through a glass block. So basically, that's the content for this evening. So let's just begin. Of course, all of you at home can play along. So a pair of metal tongs are carefully held in the yellow flame of a Bunsen burner for 5 seconds. So what we have here is a kind of effectively that kind of safety flame, the yellow flame. We've got a pair of metal tongs. I'm pretty happy with this picture. That took a long time to draw this. And once removed from the flame, the tongs emit electromagnetic radiation. State what part of the spectrum this radiation is likely to be from. So everybody out there, you can play along in the chat if you want to. You put these in 5 seconds into a yellow flame, you take them out. What part of the EM spectrum will the radiation likely be from? So we've got free maths lessons, Anissa, Super Gaming. Great to have lots of people in for the stream every single evening, all saying infrared. Okay, so yeah, the answer for this is, let's write in blue, is infrared. Okay, so the word infra basically means below, and the word ultra basically refers to beyond. So what we have is a part of the spectrum which is below the visible part of the spectrum, so it's infrared, as opposed to ultraviolet, which is beyond the violet. So infrared, IR, is also suitable. That's the type of radiation which is emitted. Okay, and basically any object above absolute zero is already emitting some infrared, but the warmer that object, the more infrared it actually emits. And of course, when we get things hotter, that's what we're going to discuss in this thing here. Somebody talking about the electromagnetic spectrum song. Yeah, I think it is a piece of musical genius. So yeah, if you haven't already seen it, I'm sure you have, but go and just learn the electromagnetic radiation song, talking about all the parts of the EM spectrum. This is a question which is a paper 2 style question for GCSE, as it says down here. So this is a part of the GCSE stream. This is an AQA paper 2 style question. But of course, I appreciate that some people out there might be doing things like IGCSE for EdXL, where you might be asked questions like this on the kind of first paper. Okay, the Bunsen burner is adjusted to the blue flame. The tongs are seen to start glowing white hot after they've been held in the flame for several minutes. So before, we had something for about 5 seconds, so it only heated up a little bit. Now we've got something that has got really hot because it's been in there for several minutes. State which parts of the EM spectrum the radiation is now from. So which parts? So it's going to be more than one part. Well, first of all, because we have something above 0 or absolute 0, then that's going to be infrared, as we had before. So we're going to still have infrared radiation, and also we're going to have visible radiation as well. And we know it's visible because it says up here it's white hot, and therefore white light is being emitted. Okay, now I would say it's unlikely to have ultraviolet radiation. Okay, so I'm going to say probably not UV. Okay, UV is maybe when things are even hotter than that, so when they're beyond this white hot kind of colour. Maybe if something's being welded or something which is super luminous, but I'd say that probably the tongs, they go white hot, but I wouldn't say it's necessarily ultraviolet. Okay, we've got some acronyms here. So Joe Smith 746 says their favourite EM acronym is Raging Martians invade Venus using X-ray guns. Do you know what? I like the fact that you've got X-ray guns in there. That's right. Okay. Okay. Do you know what? I'm going to write some of these down. So we've got Raging Martians. Invade Venus using X-ray guns. Okay, I really like that one. Anissa Madava says red meat is very unsafe except giraffe. I like that one as well. So red meat is very unsafe except giraffe. Okay. Okay, Joshua Carty, excellent. Rock music. Is very useful for experimental goats, or I guess of course you could have giraffes there. So whatever you can remember, just so that you've got this idea about the order of the parts of the EM spectrum, that's really useful. Okay, I'm sure there's many more. So yeah, some nice ones there. So we've basically got, when something is really hot, it's not just giving it infrared, it's giving out visible light as well. Okay, by the way, if anybody hasn't already clicked the like button, then do just click on that like button. I think in the chat you can like click the heart button, and I think for whatever reason, if you do that, lots of things sort of come flying up at the sides, but do click the like button as well. Some of these questions do get harder. Okay, tick the correct box that describes the relationship between the peak wavelength of the wavelength emitted in parts 6.1 and 6.2. So we need to think about the wavelength of these. Okay, so the peak wavelength from part 1 to part 2. So we've got really then to think about the different parts of the EM spectrum. Now infrared is going to have a longer wavelength than the visible light. Okay, and that's just because it sort of comes first, you know, to this side here of the EM spectrum. Thank you very much, by the way, everybody, for all the likes. Really do appreciate that. Thanks so much. So the peak wavelength to the answer to 6.2 will be shorter than this. So we can see here we've got a fairly long wavelength when we've got infrared. When we go to visible light, the wavelength is shorter because it's got a higher frequency and it carries more energy. And therefore, the answer to 6.3 is the wavelength of this will be shorter than the answer to 6.1. So that one there is the correct answer. Okay. Right, the next thing is a little bit more tricky, and I think that this is kind of like pushing in the sort of 7, 8, 9 grade. This is kind of like a kind of AQA triple science kind of question. So sketch a curve on figure 9 to show the radiation emitted by the tongs after they've been in the blue flame. Okay, so basically what we have is when you've got the tongs in the yellow flame, we basically get a curve that looks like this. Okay, now we know that when we've got the tongs held in the blue flame, they emit visible light. Okay, so I'm going to start my curve down here. The other thing is that the peak wavelength is going to be shorter. So here we've got the wavelength getting longer. Have my hands just frozen? Okay, those are not my hands. Let me just see if my camera's stopped working. This is the first technical issue I've had so far. Okay, let's see if that's working. Okay, no. Yeah, exactly, free maths lessons to normal. Right, so apologies about that. This is a problem with like live streaming. It's like so difficult. Okay, you can hear me. My hands are moving. What I didn't want to do was kind of lose the stream. So yeah. Right, so loud and clear. Okay, so where were we? Right, basically, what we have here is a curve where we need to show the light being emitted by the tongs after they've been in that blue flame. Now they're going to be giving out infrared, which is this part over here, whether it's a long wavelength. Where it's a shorter wavelength, it's going to be visible, and therefore we must have some radiation emitted. And basically what we have is a shape that looks a bit like that. Okay, now this one over here I think is a little bit tricky, but what this shows is that the peak wavelength, when we had it in the yellow flame, the peak wavelength was kind of somewhere over here. Now the peak wavelength is somewhere over here in the visible part of the spectrum. Now the other thing is, the other thing is that we've got visible light. Now if that's infrared, we've got Richard of York gave battle in vain. So we've got red light all the way through to violet light over here. Now effectively at the moment it's giving out red light, and it's giving out orange light and yellow light and green light and blue light and indigo and violet. And when you mix all of these colours of light together, what we see is white. Okay, if you had something which was a little bit cooler, then the peak might be slightly further to the right. In that case, so maybe we had something which is a bit cooler. It might have something like this. And when it's a bit cooler, then we're going to be giving out things like red light, orange, yellow and green, but maybe not any blue light. And if you mix green light and red light together, that makes yellow. So this thing here appears to be white. If you had something a bit cooler, this would give out this kind of sort of yellow colour. And if it's cooler than that, then the peak might be further over here in the red part of the kind of visible spectrum, and then it would glow red hot. And that's why we find that when you've got something which is hotter, it goes red hot to yellow hot to white hot. So even though stars might be giving out lots of different colours of light, the really hot stars tend to be this kind of big white colour. Okay, so that's why as things get hotter and hotter, they eventually give out white light. And it's only if we have things which are super hot, maybe like if something's, you know, like a star or a sun, then actually the peak is over here in the UV part of the spectrum. And so something like sunlight, because it's so hot, it's going to have the peak in the UV or the kind of visible part, and it's going to be giving out ultraviolet radiation as well. Okay. Oh, cool. Somebody's actually had a similar question. Thank you to Subskill. I'm the best science teacher. Thanks so much. Hopefully some of this is starting to make sense. What about sunbeds? Okay. So what's the correct answer? Yeah, sorry. The correct answer, because I've put too many things in here, the correct one is the one I'm just going to do here in black. So this one over here in black is the correct shape. So basically we only have it in the visible part of the spectrum, it peaks in the visible, and it's higher up than this one down here. Because effectively the total area under that graph is related to the power or the energy transferred per second. And when something is hotter, there's going to be a bigger area underneath that curve because more energy is being emitted per second. Okay, do I need to shout out Mr. Barry? Hello, Mr. Barry. Hope you're doing good. Okay, define a perfect black body. So this is something that everybody here needs to know about. Okay, a perfect black body, the definition, if you are doing triple science, is basically a perfect black body. It absorbs all the radiation that you shine on it, and it is also a perfect emitter. So, a perfect black body, this absorbs all the radiation incident upon it, and is also the perfect emitter. Okay, so this is a definition that you just need to know. So what we talk about is and this is maybe more of like a triple science topic for those doing, maybe 3 GCSEs. So this is also kind of linked to the Leslie Q practical, CHOP ATR. Yeah, because basically, if you've got something that's got a black surface, it absorbs radiation really well, but also black is the best emitter. Okay, the can of beans was the one that I did. Yeah, so actually, let me just get that. So you can use a Leslie cube. I did the same thing with a can of beans, and basically just take the label off. I painted half of it with a very, very thin coat of matte black paint, and what we find is that if you put water in here, and then you look at the amount of radiation emitted on each side with an infrared thermometer, then basically this one here, the black side, will have a much higher reading because it's emitting more infrared. Okay, so yeah, basically this was my Leslie cylinder with a shiny silver side and the black side, because ultimately that's all we really care about. We don't really care about kind of sort of the white side or whatever. Okay, so that was the end of that question. Right, the next one. We don't have much time because of my technical issues. The first bit is, what do we mean by refraction? Okay, so refraction is not just to do with light. Lots of different waves refract. So we can have like radio waves that refract, we can have sound waves refracting. But basically, what we're talking about is a wave changing direction as it passes from one medium into another. Okay, so I would say that we've got change of wavelength at the point of incidence. Yeah, that's a nice one. Yeah, it changes speed, but then it changes direction as well, I guess. Passes through a different medium with different densities. Zeno, yeah, I think that's true. I think what we're talking about, though, is often if it's light, we're looking at the optical density. So it's not always the density which would change it, but I guess I see exactly what you mean. But I just talk about going from one medium into another. We then have this thing here where we've got the kind of a standard block of glass that you get. And here again, as somebody says, frequency is constant. Yes, it's only changing the wavelength, and it might be changing the wave speed, but not the frequency of that wave. Okay, so we've got a ray of light. It hits the side over here. We can see that it changes direction because of refraction, and also there might be this kind of like slightly partially reflected thing from that surface. And the next question says, measure the angle of incidence as the light enters the glass. Okay, so in order to measure the angle of incidence as the light enters the glass, what I'm going to do is get my brand new protractor. All of you, make sure that you do have your protractor, because you might need to measure an angle in paper 2. Now, the first thing I'm going to do is where that ray of light changes from one medium into another, I'm going to go to this point here, and I'm going to very precisely mark out from this point 90 degrees. Okay, Now the reason I'm doing that, and I'm going to do it in a pencil, I'm just going to do maybe like a dotted line here. The first thing I'm going to be doing is drawing the normal at 90 degrees. Okay, if you don't have a protractor, somebody says they love tractors. Yeah, if you don't have a protractor, go and buy one. The next thing we then need to do is just measure the angle. And I reckon, as I'm doing this, the angle that we're getting, looking at my protractor, I reckon down here, if I just zoom in a little bit more, that's equal to about 30 degrees. And therefore, I think that this angle here, the angle of incidence, I, is equal to 30 degrees. Okay, so yeah, so basically for the next answer, the angle is 30 degrees. And often they'll maybe give you a bit of leniency, maybe plus or minus 2 degrees, depending on that. Right, is the workbook free? No, but it's not very much. So if you want to get hold of these questions, you also get the mark scheme and work solutions. And if you've got a school subscription or premium plan, then you can also see full videos where every answer is worked through, that you can sort of work through at your own pace. Okay, okay, right, so we've measured that angle. Describe what happens to the light as it enters the glass. So basically what's happening here is as the light enters the glass, and if I just kind of put in and kind of continue this line going through here, what we can see is that the angle of refraction, R, is smaller than I. So we can see that R is smaller than the value of I, and that means the light is bending towards the normal, so it's slowing down. Are these live streams every day? Yeah, these live streams are basically 5 days a week at the moment, and you can see my plan for everything that's coming up, like tomorrow night and the next night and the next night, but not Friday or Saturday. Okay, describe what happens to the light as it enters the glass. We can say that the light slows down. It bends towards the normal as it changes direction. Okay, so that's basically what happens when we have refraction. Okay, am I doing A-level physics? I will be doing A-level physics in about 5 minutes time. Yeah, there was a stream yesterday on Sunday night, and yeah, if you want to catch up on that, you can do just by going to my website or just looking on YouTube and so on. On figure 11, drawing the ray as it emerges from the glass and enters the air. Well, the important thing here is we have parallel sides, and that means as the ray of light enters the air, it's going to speed up and it's going to move away from the normal if we were to draw it here, and the ray of light coming out would be parallel to that ray of light coming in. So probably the quickest way to do this is just kind of, I guess, I could measure the angles, but I'm just going to judge it by I. So I can see that this bit of the ruler here is parallel to this, and what we'd have is something like this. Now again, what it's often useful to do is to maybe label extra bits on your diagram. Okay, and if we know that that angle of incidence is 30 degrees, the angle of refraction here as it goes into the air is going to be 30 degrees as well. So that shows that even if it isn't exactly precise, I'm trying to do that. Okay, right, so the normal is the line that is at 90 degrees to the surface where the ray of light hits it. Okay, so the normal line is just at 90 degrees to the surface. Okay, and of course you can measure that using your protractor. So we've done that one there. Describe the properties of ray 3 and explain why it's produced. So why do we have ray 3? Well, basically, what we have there is a ray of light that's been reflected. And here, this angle here, I'm going to call it R, and that's equal to 30 degrees. But here what we have is we have reflection. Okay, because sometimes when you've got this kind of flat side, not all of the light goes in. So this is the reflected ray. So what I could say is that we can say that ray 3 is the reflected ray from the glass surface. And we can also say that maybe the angle of incidence is equal to the angle of reflection. Okay, so two things there that we can say. Right, there we go. I think I've actually finished kind of pretty much bang on time, despite the technical issue we had earlier. So basically, questions like this, they're not always that bad. Okay, that was the last question we did for GCSE. So tonight we've done some stuff about reflection and refraction, the importance of using a protractor, and make sure that you do invest a good kind of 50 pence on a nice one. These Helix ones are brilliant, and you know, why not treat yourself, get a nice new one so it's easy to actually read the numbers. The other thing that we did tonight was we looked at different ways of remembering parts of the EM spectrum. So raging Martians invade Venus using X-ray guns. Red meat is very unsafe, except giraffe. And rock music is very useful for experiments on goats. There we go. Right, treat yourself. Okay, and I think it is now time for A-level. So thank you so much to everybody who's just been in the GCSE stream. Of course, if you want to catch up on anything, you can do by going to gcsephysicsonline.com/live. And of course, I'll see everybody at 7:30 tomorrow. For everybody joining from A-level, there's one thing I need you to do tonight. Now, obviously, I do charge for some content on my website, you know, and I've got loads of stuff for year 13. Uplearn charge you a lot more for pretty much the same content. But basically, if you go to my website, what you can do is you can download this derivation book. Okay, so it's called A-Level Physics Derivations, and basically on my website I've got videos, and I've also got worksheets which have got basically 3 parts. So the first worksheet tells you what to do, the second worksheet gives you a bit of scaffolding to start you off on that derivation, and the third one actually has information about how to answer it. Now, within the booklet itself, I've got all of these derivations here. So if you're doing A-level physics, then some of these should be equations that you're familiar with. Okay, so looking at capacitors in parallel and series, the distance of closest approach, if you maybe have like particles kind of coming towards each other, useful for things like estimating the radius of the nucleus, kind of some like year 12 stuff and plenty of year 13 things. Now, not all of these are going to be useful for everybody, but lots of these are going to be useful, you know, maybe if you're doing AQA, certain options. We've got how to derive centripetal acceleration, lots of good stuff here, escape velocity. You know, this is kind of good stuff in A-level physics. Now, showing you what's inside, what I've tried to do is use different colours. And if we've got a bit of time, we can maybe have a look at some of these later in the stream. So, for example, here's one that kind of looks at gravitational attraction and how to derive F equals minus GMM over R squared, or G equals GM over R squared. We've got orbital period and radius, so T squared is 4 pi squared R cubed over GM. This one here I think is a nice one. Actually, this took a lot of time to get all of this onto one page. So showing how the centripetal acceleration A is equal to V squared over R. It's basically using this and this and this, and this is just an approach that you can take. Now, some of these derivations are for the first year, some of them are for the second, but this is completely for free, okay? So you don't have to pay anything, but of course, if you go to physicsonline.com/a-level-derivations, there's a link to it in the chat, and I'm going to put a link to the description underneath the video. I'll put a link in the comments as well. You can download all of this completely for free, and I think it might be quite useful as you're doing your revision over the next few weeks. Now, the actual work we're going to be doing this evening, it comes from my daily workout, book 4. Ideal if you're in year 12. Year 13, it's probably too late to buy this now. You've got other things you need to be concentrating on. But year 12, buy this book and then work through it once you get to the end of year 12. And this will set you up really well for the start of year 13. It kind of covers things like logs and natural logs, It covers some of the kind of practicals you're going to be doing in year 13. There's basically lots of good stuff here. And I'm particularly happy about this diagram that I drew looking at gears, although it's actually a question about natural logs. Okay, right, so the question we're doing today is based on one on the 30th of July. If you want to download this, then you can do that by just going to alevelphysicsonline.com/live, and you can download the worksheet which just has these two questions, so you can get hold of this. So the first bit is looking at taking the natural log of both sides of these equations. Okay, now if you're in year 13, you should know how to do this. Okay, so let's have a look. So if you want to take the natural log, I'm going to call it ln at times. People happy with that? Yeah, so I'm going to call this ln just to make sure that I'm not talking about log, which I kind of tend to refer to. If I talk about log, it means log to the base 10. If I talk about natural log or ln, I'm talking about this. So basically, the first one is ln y is equal to, we'll tell you what, oh yeah, somebody says ln is the best way to pronounce it in the chat. What's this equal to? So all of you can type this in. There's no special characters. So everybody playing along at home, all of you A-level kids out there, the year 13s show the year 12s what to be doing. Year 12s, if you're doing A-level maths as well, then show the A-level physics only students. What's this equal to? What's the best way to actually write this? So we're going to take the natural log of both sides of that equation. ln is natural log 0. Yes, it is, yeah. So we've got ln n plus x. Yeah, ln y equals ln n plus x. Yeah, I think people have got the right idea here. So basically, because we're going to take the natural log, we're going to bring the x down, and then we're going to add the natural log of n to x. Okay, so first of all, that one there is a very mathematical thing. Okay, the second one, what's the answer going to be now? So we've got a equals a naught e to the nx. Okay, so I'll start you off. We've got ln a, and that's going to be equal to, what do we reckon? So why don't we multiply? Okay, people have all got different answers. I reckon, yeah, the answer should be this one over here. Now, some people might not have seen this, and basically, this is stuff that you do in year 13. Okay, and we've got somebody saying, so light Arjun, we've got the first correct answer, fantastic. So that's going to be equal to the natural log of a naught plus nx. So whatever's up here, because we're taking the natural log, we bring this down. Okay, and then we add the thing that it's multiplied by, so we add that onto that. Okay, so we've got a few people maybe not being that careful. Ln e is the same as x. Okay, this is more confusing to teach. I guess I sort of went straight in. And if you're year 12 and you haven't seen this before, don't worry about it. That's absolutely fine. Okay, so based on this, if we're going to take the natural log of both sides of this, the next one, the natural log of d is going to be equal to, because last time we had the natural log of a plus all of this, we're going to have the natural log of d naught. But now we've got e to the minus nx. And basically, if we're taking the natural log of e to the minus nx, that is then the same as minus nx. So now rather than plusing nx, because effectively there we had plus nx, now we've got minus nx, it's minus nx. Okay, so who's got the right answer? Now, ln d equals ln d naught minus nx. Light Arjun, Drav Anil, yep, perfectly. Right, now, if you don't understand this, that's absolutely fine, but I'm going to give you a chance to have a go at the last one. The last one is d is equal to d naught e to the minus kn. So based on what we've seen up here, what do you reckon the last one is? And I know lots of people are going to start to get confused if you're year 12, which is absolutely fine. But I'm going to show you something in the book that might be interesting. Okay, so we've got Light Arjun again saying ln d naught minus kn, ln d minus kn from Isa Ahmed. Yes, okay, so this one here, we've got ln d is equal to ln d naught minus kn. Okay, and that's all it is. Isabella Webster, yep, excellent stuff. Now, this looks quite difficult when you first do it. But what I've tried to do with these books that I've made is I can teach all of this to you from scratch. So what I have is basically questions in the book that kind of lead you up to this. So if I show you on the 24th, we want to take the natural log of both sides of these equations. So if we've got y equals e to the x, we can then say that ln y is equal to x. And if you're not sure, you can obviously look at the answers in the back of the book. The next one is y equals e to the 2x. So the natural log of y is equal to 2x. The next one, the natural log of y, we've now got e to the nx. And if that was just a number in front of x times x, we've now got n. So that's equal to nx. And if you've got y equals e to the 2nx, that's just equal to 2nx. So what I've tried to do is build up stuff very gradually in the book. And that means if you actually have a go at this yourself, it's maybe a little bit difficult to see. It's a little bit blurry on that kind of sort of zoomed in shot. So basically you can kind of do questions like that. It builds up on the 25th, builds up on the 26th, builds up on the 27th, builds up on the 28th. There's then a chance for you to give me a 5-star review on the 29th. And then on the 30th, we have these different things that you might not have seen before. So the idea in this book here is that you can basically teach yourself everything. And that means when you start in September in year 13, suddenly you're like, I know how to do this. I've been doing it all summer. And this is going to help you get the high grades going into year 13, and then hopefully for your exams at the end of it. Okay, so we've got some information there. Now we've got another question. We've got 100 dice thrown into a container. Those that landed with a 1 or a 2 showing were removed, and the remaining dice were thrown again, and so on. So this was the data recorded. So after 0 throws, about 100 we started with 100. After 1 throw, because there are 6 sides and they're kind of normal dice that aren't biased, if we remove the 1 or a 2, that means about a third of the dice are going to be removed. So effectively what we've done is we've got rid of 36 dice. And then after the second throw, 46 remained. So about 2/3 remained after each throw. The first thing we need to do is we need to plot this data on a graph. Okay, so here's the axes already shown. We've got the number of throws, n, and we've got the number of dice remaining, d. Okay, so let's have a look. So when after 0 throws, we had 100. After 1 throw, we had 64. So if that's 70, that's going to be 64 there. After 2 throws, we had 46. After 3 throws, we had 29. After 4, we had 19. After 5, we had 14. After 6, we had 8. After 7, we had 5. And then it was 4, 3, and 2. Okay, so all that we're doing at the moment for this first thing is we're just plotting some data. Okay, and then we, of course, if we plotted data like this, we can see it's definitely not a straight line. So what we need to do is we need to put in a curved line of best fit. I would suggest using a pencil, putting your hand on the inside, and then we get a shape that looks a bit like that. It's a bit lumpy in the middle, but this is the idea, and I think that's good enough for any kind of exams you're going to be doing. So we've basically plotted the data and drawn a line of best fit. Use your graph to estimate the half-life, giving it as a number to 1 decimal place. So looking at this data here, what do you reckon the half-life is for the decay of dice? Okay, so again, even if you are year 12, I mean, if you're year 13, you should know how to work out the half-life quite easily. If you're year 12, then you will have done this when you did GCSE. So looking at the graph here, let's see what people's estimations are. What is the half-life, using my kind of rough line I've put here? What do you reckon the half-life is? 2.25, somebody's saying. I'm not sure if that's correct, Josh. I think it's a good start. You're the first person to type in. The measure at 50, somebody's saying 2. 8.6, that's not a number. 1.8, 1.6. Okay, I think we're getting into it. So the way to work out the half-life, yeah, never mind, you read it wrong. Okay, the half-life, it starts at 100. How many throws does it take to get to half of that? And so if that's 100, we're going to just draw a line off over at 50. And I know my line isn't the best, but we're just going to use it for the moment. And if I draw a line down, we've got an answer there of about, roughly about 1.7. Okay, so I reckon using this, we can see that after, on average, 1.7 throws, the number of dice goes down to half the original amount. Of course, we can check it again. So if it goes from 50 and it halves again, it goes down to 25. So that's 36, 25. And if we draw a line across there and we draw a line down, that number there is about 3.3 or 3.4. So it's about 3.4. And so what we can see is over the same kind of period, the same number of throws, it goes down by half. If we did that again and we looked at 12.5, which is going to be here, something like that, we draw the line down. Oh, there you go. Not the best line down. That looks to me to be about 5.1. So what we can see here is an example of an exponential decay. Okay. In actual fact, if we say that the number of dice remaining is D, that's going to be linked to the number that we started with. And the number that we started with, we could call that D0. So that's the original number of dice. And the number of dice left D depends on the number of throws N. We can also see that we have this exponential decay because over the same time period, it halves, and it halves again. So we're going to have some kind of exponential decay. And we often represent that as y equals e to the minus x. Okay, I would say in this example, we don't have x. Instead, on the x-axis, we're plotting n. So we've got e to the minus n. And we're going to multiply that by the starting value, which was d0. And that's going to tell us the number of dice after a certain amount of time. But the thing here is that what we don't know is the constant, which is to do with the number of dice being removed each time. So we're going to call this unknown constant k. So what we can actually do in this example over here is we can fit what maybe initially looks like quite a complicated equation to some simple data just about dice decaying as they're thrown. Okay, and we can use this thing here to actually work out the value of k, which is going to tell us things like the half-life or what the half-life should be. But we're going to be doing another question about that on Wednesday's live stream. It's Monday today, isn't it? So we're going to do another question about this on Wednesday. And if you look in the book, you'd see that actually the first part of this question is the one that we've just done on the 30th. And on the 31st, there's a similar question that asks you to do a little bit more to actually work out things like the constant of proportionality in that case. So we're going to do that and kind of take this knowledge a little bit further on Wednesday's live stream. Does that make sense? Or have I just really kind of lost everybody? Initially, though, we started looking at natural logs, and then we've plotted some data and used that data to find the half-life for that particular dice which is decaying. Okay, Right, the next thing we're going to do now is we're going to look at some derivations. Do you want to see the derivation for orbital, period and radius, or would you like to see the derivation for radioactive half-life? So let me know in the chat and I'll go through whichever one the people watching would like. Would you want to see orbital, period and radius, or do you want to see half-life and the way that you can actually derive either this equation or this equation? So just say orbital, period or half-life. Tommy G is half-life, Jacob half-life, Isabella half-life. Okay, we've got an orbital, radioactive half-life from Light Arjun, Smokes orbital, the real Joe Linton, hello again, half-life, Ajwa Gul, half-life, orbital period, Leela. Okay, so he says I'm legend, thank you very much. Jamil, orbital, football fandom, half-life, Phil G, orbital, Nicola, half-life. Okay, I think about 2/3 or about 0.673 of you are wanting the half-life. So this is kind of sometimes an equation given to you. Now, basically, this sheet just says, derive the expression for the half-life of a radioactive isotope in terms of its decay constant. Now, there's two ways you could start. We have here just this exponential decay, like we saw in that last question. And maybe let's think about the activity of that sample. Okay, so maybe it starts at time equals 0. So this is maybe time along the x-axis. Okay, we've got 0 up to whenever. And after a certain amount of time, this goes to a certain value, which is A, after a half-life. Okay, so what we can see is the initial activity falls to half of the original amount after one half-life. Okay, so I'm just going to kind of put that into this. Okay, now the equation that links activity to the original activity is A is equal to A naught times e to the minus lambda t. Okay, now that means we can find out the activity at any time, but there's going to be a special case where when the time is equal to the half-life, t1/2, we know that the activity is going to be equal to half of the original activity. Does that make sense? Hopefully this is all making sense so far. So this is the equation that you get given in your data book. We know when the time here is equal to t1/2, then the activity here is going to be equal to the initial activity divided by 2. So I can put these in to say that when the initial activity over 2 is equal to A naught e to the minus lambda t1/2. Do you see what I've done there with the colours? We can actually simplify this a bit more because we've now got an A naught on both sides, and that means that they cancel. So we can say that a half is equal to e to the minus lambda t1/2. Okay, we can then take the natural log of both sides to say that the natural log of a half is equal to minus lambda t1/2. And again, this is why I kind of started doing work on natural logs, which I think hopefully if you're in year 13 you're following this at the moment. Now the other thing is that the natural log, I'm just going to put this over here, the natural log of a half is equal to, is it minus the natural log of 2? Okay, so we can also really write this over here as minus the natural log of 2 is equal to, this is probably an extra step you don't need to include, and therefore what we can say is the natural log of 2 is equal to lambda t1/2. And if we want to find out the value of t1/2, that's going to be equal to the natural log of 2 divided by lambda, where lambda is just that decay constant. Okay. Sometimes, of course, you also see this written down as 0.693. Let me just check that. So 0.693 divided by lambda. Okay. Yeah, so basically, I reckon you can do all of that in about 30 seconds if you practice it. Okay, there's a lot of writing, but I suspect a lot of the time you don't necessarily need to include all of these other steps I've put over here. So you can basically write down all of this in about 30 seconds, and I think it's just a good kind of skill to practice. So that's for everybody out there. For initially, we've got a lot of people asking for the one about half-life, so that was dedicated to Tommy, Jacob, Isabella, Light Arjun, the real Joe Linton, Ajwar Gul, Afia Lutin, Football Fandom, Nicola, Zoe, both, Tommy, yeah, okay, we'll do the other one, Half-Life, yeah, so there's so many people out there who said that. Yeah, from Smokes, right. The next one then, we're going to do something which I think is a nice one. So this is about the relationship between the orbital period, which is t, and the radius that a smaller object is orbiting a larger body. And sometimes we just want to show really that t squared is proportional to r cubed. Okay, so let me just put this over here. Just going to get a quick bit of t. Yeah, sometimes known as Kepler's third law. Some exam boards actually look at Kepler's first and second law as well, about like the area swept out over equal time periods. But a lot of them refer to this equation, but they don't actually refer to Kepler himself. So this is Kepler's third law. So the first thing we can look at is the size of this force. Okay. Now the size of that force here, it's due to the gravitational force of attraction, and that's going to be equal to gmm over r squared. Okay, and that's from Newton's law of gravitation. And I've left out the negative sign because it's the magnitude of the force that we're interested in. Now that force is going to be providing a centripetal force as well, which is equal to mv squared over r. And here it's going to be small m because that's the object which is accelerating in that circular path. AQA doesn't require Kepler's first or second laws. Okay, so we know the size of this force is due to Newton's law of gravitation, which is equal to the centripetal force. And we can now equate these two things together. We can see that some things simplify, so I'm just going to get rid of that for a sec. We can see we've got an r squared and r, so I'm just going to get rid of those. And we've got an m and an m. So if I rewrite that, we can say that's equal to gm over r is equal to v squared. So how do we know the velocity? Well, we know that, I'm going to go into green, we know that the velocity of an object in a circular path is equal to the distance travelled, which is one circumference of that circle, so that's 2 pi r, divided by the time period. And that means v squared, if we square both sides of this, is equal to 4 pi squared r squared over t squared. And we can now put this back into that to say that gm over r is equal to 4 pi squared r squared over t squared. We can bring this r up over here and bring the t squared up over here. So let's say t squared is equal to gm, sorry, we can say that t squared times gm is equal to 4 pi squared. We've got r squared times r, so that's going to become r cubed. And if we want to make t squared the subject, we can say that t squared is equal to 4 pi squared over gm times r cubed. Okay, and of course, if we have something where we've got the gravitational constant and the mass of that big planet, 4 pi squared over gm is going to be a constant, and therefore t squared is proportional to r cubed. Okay, so you could probably do that derivation using omega is 2 pi over t, maybe, but I don't know if you need to. So yeah, I think that's the way to show it. And if you actually look, oh my god, that's quite similar to what I've done previously. If you download the derivation booklet, it shows the same thing, which I've got over here, which is basically just like a digital version of this. And of course, if you want to get that derivation booklet, It's got all of these derivations in it for you to just learn and actually practice, so you can have a go at a lot of the things that might come up in your exam. Some of them might be in the specification, and it's always worth checking your own specification to check exactly which things you need to derive. But being familiar with them means that if something similar is given to you in the exam, it's much easier to derive that equation because you're familiar with some of the kind of ways that you do that. I think that's pretty much it. Kinetic theory derivation. Do I have one on kinetic theory? I do, yeah, I think third from the end. I do have, here we go, kinetic theory, to show that PV is a third NM C bar squared. So I've got all of that. I think that's a tricky one to get onto one page. So if you're not sure about kinetic theory, about how you've got the change in momentum as a molecule collides with the side of a container in maybe a cube, that's all there for you to download. The link is in the pinned comment. You do subscribe to my newsletter where I will bombard you with useful stuff every single week. I basically do an email newsletter on a Sunday. Lots of people like it. Thousands of people are watching that. The other thing that thousands of people are doing, and by the way, once you finish this, if you go to my YouTube channel and you look in the community tab, you will see my daily questions. So I'm giving out GCSE and A-level physics questions every single day. I can't remember what time I put them out today, but I think I had a GCSE one in the morning and I had an A-level one this evening. About 1,000 people just like you are having a go at that question every day, and there's going to be one every single day between now and your exams. Finally, what kind of ruler is it? It's a helix one. I can't remember the model, but it's really useful because it's got one side which is good for drawing lines best fit because it's clear, and the other side is metal, which is just a really nice kind of thing. Okay, yeah. Right, that is it. That is the end of the live stream. I hope all of you are doing okay. I will be back here tomorrow. Tomorrow, we're doing something from book 3. I can't remember what, but if you have a look at alevelphysicsonline.com/live, you will find the worksheet that you can complete in advance. You'll see the questions, and we're going to be doing, I know what we're doing. We're doing G by freefall. No, we're doing G by the trapdoor method. Hopefully that will help. Thank you, everybody. Sorry I couldn't mention everybody from the chat, but it's great to have so many people here, and I'll see you again tomorrow. Good night.